Okay, so I would try to derive the Lagrange multiplier method from implicit function theorem. I made this video because I was very confused in lecture how the lecturer derived this. Yeah, I'm just gonna try to do it. Okay. So first, if you have a function like x of xyz equals to xyz, and then you have g of xyz equals to like x plus y plus z equals to 1, say, and then we want to maximize this function with subjected to this constraint. Now, as Monty said in class, this has a definitive answer because we're in a closed bounded set, right? And then um, the best way to solve this is just to solve for either x, y, or z in terms of others in this case, and then we plug in into that f, and then we can maximize just with respect to, we just maximize this or minimize this if you want to, using just gradient of f with respect to y is equals 0. Now this is, so we just turn a constraint problem into an unconstrained problem by setting gradient equals 0, and this works, right? Because y and z can be any values now because I get rid of x, right? And then but this method is not general enough because sometimes the g cannot be, I mean the variable x might be very hard to solve for in terms of y and z. So that's where the implicit function comes in, right? So the implicit function tells us that if you have a function, say like g of y x y z equals to a constant, and then say if del g of over del x is not 0, then we can solve x in terms of y and z differentiably, of course, provided that condition. And now we're gonna make a simple assumption. We're just gonna try the 3-variable case, but the method, of course, generalized easy to higher dimensions. But just for illustration, I'm gonna think about a general problem where I'm gonna maximize f, y, and z. Max or min actually doesn't matter, right? Both are done by the same condition, and then subjected to g of x, y, z equals to some constant. Now I'm gonna make an assumption that gradient of g is not equal to 0. So okay, so all this, I mean I'm deriving a condition of point x0, y0, and z0. I'm deriving a condition for that point. On that point, the relationship between f and g and their gradient, such that this point can be a critical point, right? So just bear in mind that when I say x and y and z here, gradient, I mean the gradient, I'm sorry, when I say gradient is not equal to 0, I mean gradient at this specific point is not equal to 0, not in general, right? That's not correct. So gradient of g is not 0 at this specific point. So we know that del g del, so if gradient is not equal to 0 vector, that means some component of it, either x, del g del x, del g del y, del g del z, one of this has to be non-zero, right? If all of them are 0, then the whole vector is 0, then so that's not our assumption. So one of them is 0, right? So sorry, without a loss of generality, I'm just gonna say without the loss of generality, assume that del g of del x is not equal to 0. I mean at this point, right? We're deriving this at a specific point, but I'm just gonna use symbol x here. Now this gives us our advantage to use the implicit function here, implicit function theorem here. Now if del g del x is not equal to 0, we know that del g over del y can be, del x over del y can be expressed as negative del g del y over del g del x, and then del x del z will be equal to negative del g del z over del g del x, of course. Now del g del x, of course. Now we want to plug this kind of condition into our f, right? But of course we're not able to do that because sometimes we can solve it explicitly of x in terms of some function of y and z, but we've done so differentiably, right? We got our del x, del y, del f, del z, although we don't have a formula for that. So we don't actually plug that into f, but we just calculate. So imagine that we somehow reduce f in terms of just y and z. Somehow we plug x in here, right? We plug x in here. Now, actually, sorry, I'm gonna say x in terms of y and z implicitly, and then we have y and z, right? So now we just have two variables, right? So we calculate the gradient of this, and we set it equal to 0, and we are done, right? So del f del y would just be del f del y. Now this is where it gets very confusing for me. Del f del x, del x del y, right? That's by the chain rule, because we have one way to get to y directly, or get to x and then x go to y, right? That makes sense. However, these two are not the same function. These two, right? Not the same, right? This is when we consider only two variables. What I mean is we consider only f in terms of y and z when we plugged in x implicitly, and this is the whole function f, x, and y and z, the original function, right? Okay, so just to bear that in mind, and then yeah, this is very bad. Okay, so I'll help you with this. I don't know if Monty helped you with this in notes, but I'll just write this as y and z, x, y, z, right? This is original function. This is original. This is our reduced version. And then another condition, this equals 0, right? Del z, del f, x, y, z of del z, right? Plus del f, x, del x, del z equals 0. That's our condition, right? We set the gradient equals 0. We have these two functions, the equation to solve for. And then we know that del x, del y, del x, del y, and del x, del z are given here and here, right? So we plug them in, we get del f, del y. Okay, so I'm just gonna say this del f, x, y, z, del y plus del f, del x. Del x, del y is equal to minus del g, del y, del g, del x. This equals 0, and then the same for del f, del z. I'm just gonna leave that out, the x, y, z thing, and then del f, del x, del x, del z is equal to del g, del z, and del g, del x, right? Equals 0. Now this is our final condition. We're just going to simplify. Somehow we're going to simplify this into condition like gradient f equals lambda gradient g for some lambda, right? And then the way to see it is since we made the assumption here that del g over del x is not 0, I'm going to utilize that. I'm going to set, I mean, these are ultimately just numbers, right? This is just our numbers. And since del x is not, del x is not 0, I'm going to set del f over del x over del x equals lambda, just a constant. This is just my trick, right? And this is allowed because this is non-zero. This is not 0. And then we move here. We get del x, right? And then we plug this condition into both equations, and see from the first one we get del f del y equals to del f del x del g over del y del g over del x. Now we multiply both sides by this quantity. Now we get del g del x times that equals to that, right? Now we have del f of del x. Now this quantity is lambda times this quantity, right? So ultimately, which is gonna be like lambda del g del x, right? And then we just cross this 2 out. We got that, right? And by the same token, if you plug this condition into this second equation, we get del f over del z equals lambda del g over del z, right? Now we combine these three things. We get gradient of f equals lambda times the gradient of g, right? Now this is our final conclusion. If such a lambda, I mean, the conclusion is, sorry, that for any critical point, which means they have the chance to be the global minimum or global maximum in this case of constraint optimization, if they satisfy this condition, right? If you have, and of course I just done it for 3 variables, but this generalized to more than one variables, right? I'm just gonna say vector A. So A is critical if that. Okay, so sorry for the bad handwriting and stuff, but thanks.